Let's see how to do a level order traversal of a binary tree. To do a level order traversal means to visit all the nodes in the first level of the tree left to right, then all the nodes in the second level of the tree left to right, and so on all the way up until the last level. So let's see this with an example. So here we have a binary tree, and level order traversal of this tree would be 1, 2, 3, 4, 5, 6, and 7. So we visit every level left to right, starting from the first level. To do this, we will use a queue. And we start by pushing to the front of the queue the root of the tree. Then we go to the queue and we set the current node to the front of the queue. In this case, it's 1. We pop the front of the queue and we visit current. In this case, we will just print it. Then we add the left child to the back of the queue and the right child to the back of the queue. Then again, we go to the queue and we set current to the front of the queue, which in this case is 2. We pop the front of the queue and we visit 2. Then we add the left child of 2 to the queue, followed by the right child. We go again to the queue and we set current to the front of the queue, in this case 3. We pop the front of the queue and we print current. Then we add the left child, but in this case there is no left child, so we only add the right child to the queue. Then we go back to the queue and we set current to the front of the queue, in this case 4. We pop the front of the queue, we visit 4, and we try to add its left child, but there is no left child, and its right child, but there is no right child. So we're done with the 4. We go back to the queue and we set the current node to the front of the queue, in this case 5. We pop the front of the queue, we visit the current node, and we add its left and its right child if it has, but it doesn't have them. So we're done with the 5. We go back to the queue and we set current to the front of the queue, in this case 6. We pop the front of the queue and we visit current. Then we add the left child to the queue, and it has no right child. We go back to the queue and we set current to the front of the queue, 7. We pop it from the queue, we visit 7, and then we add its left child, but it doesn't have a left child, and its right child, but it doesn't have a right child. So we're done with the 7. We go back to the queue, but this time the queue is empty, so this indicates that we're done. So the output is 1, 2, 3, 4, 5, 6, 7, which is the level order traversal of this tree. Let's see how to implement this. So we'll have a function called level order, which will take the address to the root node of the tree and returns nothing. The first thing we do, we check if root is null, because if root is null, the tree is empty, so there is nothing to visit. But if root is not null, means that we need to actually do a level order traversal. So we begin by initializing our queue. We'll call it queue. And we push the root node to the queue. Then, while the queue is not empty, what we will do is we set the current node to the front of the queue. Then we pop the front of the queue and we print the current node. Then we're going to check, does it have a left child, and if it does, we will add it to the queue. So if current left is different from null, we push to the back of the queue current left. We do the same thing for the right side. So if it does have a right child, then we push to the queue the right child. And then we're done. So that's the whole function. So let's actually run through this with an example to demonstrate that it actually works. So we have the same tree we've seen before with root 1. So we call a level order passing root 1, we check is root null or root is not null. So we initialize our queue, and we push to the queue root. So we're going to add to the front of the queue 1. Then while the queue is not empty, we're going to set current to the front of the queue. So 1, we pop the queue, pop the front of the queue, and we print current. Then we're going to check, is current left different from null? The left of 1 is 2, so it's different from null, so we push to the queue current left, so 2. And then we check, is current right different from null? The right of 1 is 3, so it's different from null, so we push it to the queue. We go back to the condition, the queue is not empty, we set current to the front of the queue, which is 2. We pop the front of the queue, and we print current. Then we check, is current left different from null? The left of 2 is 4, so it's different from null, so we push it to the queue. And we check, is the right different from null? The right of 2 is 5, so we push it to the queue. We go back to the condition, queue is not empty, we set current to the front of the queue, which is 3. We pop the front of the queue, we print current, we check, does it have a left? The left of 3 is null, so it doesn't have a left. It means we do nothing. We go to the next condition. So does it have a right? The right of 3 is 6, so we push it to the queue. We go back to the condition of the loop, set current to the front of the queue, which is 4. We pop the front of the queue, we print current, and we check, does it have a left? The left of 4 is null, so we do nothing. Does it have a right? The right of 4 is also null, so we do nothing. We go back to the condition of the loop, queue is not empty. We set current to the front of the queue, so 5. We pop the front of the queue, and we print current. Then we check, does it have a left? The left of 5 is null, so we do nothing. And does it have a right? The right of 5 is also null, so we do nothing. We go back here, the queue is not empty, we set current to the front of the queue. We pop the front of the queue. We print current. And then we check, does it have a left? The left of 6 is 7, so we push it to the queue. And does it have a right? The 6 doesn't have a right. So we go back to the condition, the queue is not empty, we set current to the front of the queue. We pop the front of the queue. We print current. And we check, does it have a left? No, it doesn't. Does it have a right? No, it doesn't. So we go back to the condition. This time the queue is empty, so we exit the while loop and we exit the function. So the output is indeed 1, 2, 3, 4, 5, 6, and 7, which is correct. Let's analyze the time and the space complexity of this function. For the time complexity, initially we do some constant amount of work, then we have a while loop. Now, inside this while loop, we print the current node. Because every node in the tree will be printed exactly once, this while loop overall will run n times, and the amount of work we do inside is constant. So the time complexity associated with this loop is O of n, and so overall the time complexity associated with the function will be O of n. What about the space complexity? It will depend on the maximum size that our queue will reach. So what's that going to be? So if we carefully look at this function of what it does, we will notice that at any point in time, the queue either contains all the nodes of a specific level or the starting nodes of one level and the ending nodes of the previous level. The worst case occurs when the queue has all the nodes of the last level of a binary tree that has all the levels filled, because in that case, the number of nodes in the last level will be equal to the half of all the nodes. So the queue will contain n half nodes. Therefore, the space complexity will be O of n. You can find the link to the code in the description below.